Okay, let's start class. In the last class, we talked about the statistical inference for the binomial type data. So we talk about the confidence intervals, point estimate, right? So for the confidence interval, I focused on three types of confidence interval. One is the word test, and the other one is the score test and the likelihood ratio test, right? So the confidence interval, and I explained, so the relationship between the confidence interval and the hypothesis test. We can also do the hypothesis test. We have the word test, the score test, and the likelihood ratio test. There is a direct connection between these two, right? And we can actually construct a confidence interval through a hypothesis test. And we can use the confidence interval to do the hypothesis test, right? So the idea for a confidence interval based on a particular test is we need to find out the parameter values such that the test statistics based on this specific test will not reject the null hypothesis. And that set of values for the parameters is the corresponding confidence interval. Okay? And we also talk about how to interpret the confidence interval, right? So here the idea is the confidence interval from the frequentist point of view. Those limits, the lower bound and upper bound from a confidence interval, these are random. These are realizations of those random variables from a particular data set. And if we resample again, the constructed confidence interval will be different. Okay, but in the frequentist point of view, the parameter itself is unknown but fixed. But our confidence interval is random. Okay, and what does 95%, let's say 95% confidence interval means? That means if we resample from the population repeatedly, okay, and each time we got the random sample and we construct the confidence interval, so we can have many, right? Theoretically. And 95% of these confidence interval will catch the unknown parameter. That's how we interpret it from the frequentist point of view. But from the Bayesians, it's different. They call it credible interval. So from the Bayesian perspective, the parameters is not fixed. Okay, so it's different. Okay, and we talk about the hypothesis testing and the confidence interval through a coffee taste data set. Remember, this is we have N is 100 and we have 60 out of 100 prefers the new blend and this. Now let's see another example. This is the vegetarian example. And to find out the proportion of vegetarians on campus, we asked 25 randomly selected students, and none of them answered yes. Okay, so we want to find out the 95% confidence interval for the true proportion of vegetarians on campus. So you may ask why we need to have another example, right? We've already done the coffee blending examples. So here, the idea is that we talk about three tests: word test, score test, likelihood ratio test. But why we need to talk about these three? Because they have different performance in different situations. Okay, and the coffee tasting example, I would say, is one of the easiest scenarios for the hypothesis testing and the confidence interval. Why? Because you can see the sample size for the coffee tasting is pretty large, n is 100. That's good. Like for the central limit theorem, we usually require the sample size to be large enough, right? And usually the magic number is 30. So if it's greater than 30, that's nice. So here is 100, okay? And second is, for the binomial distribution, we have another parameter, that's the pi, right? That's the true proportion. And here we do the hypothesis through the true proportion is what? 0.5, which is very good. Why? Because we talk about for the binomial, the variance and the standard deviation depends on the pi, right? And what is the value of pi that is easiest to do the test and easiest to construct confidence interval? That happens when we have the pi is close to 0.5. And you may ask why we need to have the pi is around 0.5. Why this is the easiest or the most accurate, the best case? That is still because of the central limit theorem. Okay, because we want the sample size to be large enough. Okay, when the pi is close to 0.5, so we have the number of success and number of failure. They are both quite large. Does that make sense? So that's why when we do the when we test the binomial or when we test the proportions or construct confidence interval for the population proportions, remember we usually have some condition. What is the condition? N times P should be what? Greater than or equals to 5, right? And M times 1 minus P should also greater than equals to 5. So these are the conditions that we need. Why? Because of the central limit theorem. We need sample size to be large enough. How large is large? For the binomial case, statisticians have found that when the n times the sample proportion is greater than 5, is no less than 5, and the n times 1 minus p is no less than 5, we have a good normal approximation. Keep in mind that the central limit theorem is the key for the assumption is required for doing the word test and score test. And also likelihood, because these are they are based on normal approximations. They are not exact. Okay, we will talk about some exact case in a minute. Okay, these are all why this one follows a normal distribution. Why this one follows a chi-square with one, and why this one, they all have normal approximation plays a key role behind those tests. Okay, and this normal approximation requires the central limit theorem works in, okay, effectively. So we need to have relatively large sample size. So that's why this is the easiest case. Okay, now let's see this example. This is like one of the worst situations. Now let's see how these three tests works, right? So you can see when we compare different methods, like when you have a data set, you want to fit some models, you can try different ways. You can fit like logistic regressions, decision trees, some other model like linear discriminant analysis. We can apply multiple methods on this data, they can give you different values, results. But which one works well? So we need to know these methods, in what situation they works the best, right? So that's how we compared. So we want to put these methods into different situations to see how they works. Are they give us all the same results or they perform differently? So that's the purpose for we have doing this. Okay, so here we have a small sample size, and now it's less than 30. It's just 25. And to make the things worse, we have 0 counts. Okay, so this is like the worst case, right? Now let's see the results. So here, the word test approach, we have the formula, right? Do we have it? So here is the word test. So remember here we have 0 counts, so the P equals to what? P equals to 0, right? So this one is 0. And what about the margin of errors? This is the margin of error, is that right? But inside the margin of error, we have the P is what? 0. So that means what is the margin of error in this case for the word test? It's 0. So if we use the confidence interval based on the word test, what is the results? The word test gives us the confidence interval is 0, 0, which is useless. Why? Because it just tells us the point estimate covers the 95%. So this one, based on the interpretation for the 95% confidence interval, is saying that we have 95% of chance to catch that true values, which is just a point. This doesn't make sense at all, right? It should be not just a point, it should be an interval, right? So you can see from this example, we know that word test doesn't perform well in the small sample and not balanced case. This one doesn't work well. And you may ask why? Because the normal approximation doesn't work. NP is not greater than 5. No, that's not. NP actually is 0, right? So that's why the central limit theorem and normal approximation doesn't work here. What about the score test? Score test is, so based on the definition, we need to find out the pi 0 values to make the test statistic. What is the test statistic for the score test? Is this one, right? We want to make this one is less than 3.84, I believe. That's the critical value, okay? So this one should be less than 3.84. And here, the P is 0. But pi 0 is the set of the pi 0 such that this one is less than or equals to 3.84. Because the 3.84 is the cutoff for the chi-square with degree of freedom is 1. Let's say 3.84 is here. Such that the area on the right side is 0.05. Okay, so that's the critical value. Okay. So it's not easy to calculate. There is no closed form for the score test results. Why? Because you can check. It's very difficult to find out so it's not like word test. It's easy to find out the closed form. Does that make sense? Because here for the word test, the denominator also related to the pi. So, but don't worry, I won't ask you to calculate by hand for the word test or for the score test. I might ask you to do that for the word test, which is simple to calculate by hand. But for the word test and likelihood ratio test, these cannot be done by hand. So you can, we have the computer to do that, okay? Software to do that. So anyway, we found the confidence interval is 0 from 0 to 0.133. Okay, so this is the confidence interval for the score test, 95%. And if you think, can we check that? Yes, let's check that. So let's say the confidence interval for the based on the score test is this one. Okay, so now let's check 0.1. Why we check 0.1? Because that is within the confidence interval. So if we check 0.1, let's say pi 0 is 0.1. So that means the null hypothesis is 0.1 against not equals to, right? And if we do the test, you can see we fail to reject the null hypothesis. So you can see that is included. Okay, so what if we test pi 0 is 0.2? Then we will reject it. Why? Because 0.2 is outside the confidence interval. So if we do the test, it will reject it. But inside it, we will fail to reject. Okay. And similarly, we can do the likelihood ratio confidence interval. Okay. For doing the likelihood ratio confidence interval, so we need to find out those pi zeros, such as the likelihood ratio test will fail to reject the null hypothesis. Okay. So what is the likelihood ratio test statistic? It's the ratio between, it's -2 times the log of the likelihood ratio under the null and under the alternative, right? So we can do that, and the results is from 0 to 0.074. Okay, and so that's the 95% confidence interval based on the likelihood ratio test. And then you may ask, how can we do that in R, using R, right? For the word test, we can do that by hand. But what about these? So that's why we have the introduction lab, these handouts in the, I posted in the Moodle. You can check that, okay? So in the handouts, I give you some examples, like here the X is 4, N is 10. That means we have 10 trials for success. Okay, alpha is 0.05, and we want to construct the 95% confidence interval based on the word test. So we can do that by hand. Here by hand means I can also do that in the R. That's the pi dot hat. That's our point estimate, which is X over N, right? That's 0.4 minus the Q norm for 1 minus alpha divided by 2. So this will be what? What is Q norm? This will be 1.96. Okay, so the Q norm gives you the cutoff values from a standard normal distribution with the right-hand side is our 1 minus, with the right-hand side is alpha divided by 2, and the left-hand side is 1 minus alpha divided by 2, and that will be 1.96, right? So this is, so it's pi hat minus 1.96 times the square root of this is the standard error, or this is the variance, okay, for the, based on the word test. So we can find out the lower and the upper, okay? And then There are actually functions available in R. You don't have to do that using this. There's an easy way, okay? So the easy way is there's a library called the binom. This is a package for the inference, statistical inference for the binomial related data. So if we want to do that for the word test, you just do binom.config. That's the confidence interval. For the X is the number of success that you observed. N is the number of trials and the confidence level. That's 1 minus alpha. And the method is asymptotic. That's the word test. And you can see the results. That's the lower and upper limit. And if you want to do the score test, the score test confidence interval cannot be calculated by hand. It's not that easy. So you can use the method is Wilson. Why? Because the score confidence interval test, or the confidence interval based on the score test, is also called the Wilson's confidence interval. So that's why the method is Wilson. That's the confidence interval based on the score test. For the likelihood ratio,
Excuse
the
me,
method
Professor.
is LRT. Okay,
Yeah.
so
I have a question.
here in our example, let's see in our data set. Okay, so let's see, we start with the binom. Okay, let's see the library binom. Okay, now let's see here. In our case, we have 0 counts, 25, right? So what we can do is in the R, let's just, if we want to do the word test, okay? So that's the line of the function. So it will be just the binom.config 0 success, 25 trials, confidence interval is 0.95, right? Method is asymptotic, okay? Then return. You can see it's the lower is 0, upper is 0. Okay, so if you want to do it as a different test, let's say you want to do it as a score test, that's also called Wilson. So it's same, but just method change to Wilson. So that's the lower is 0, upper is 0.133. And you can see that's the exactly what we have here. So it's 0.133. Okay, so you can easily get that. And similarly, for the likelihood ratio test, you can also do it using the method is LRT. Okay, then it's this one. So it's 0 and to 0.07. It's this one. So you can see we can all do this in the R. And you may ask which one is better. Of course, word test is the worst. It's not giving you an interval. It's giving you a point. That doesn't make sense, right? And the score test and the likelihood ratio test, they both give you they both give you an interval, okay? But for these two tests, which one is better? So just ask yourself, do you prefer a confidence interval with a narrow range is better or a wider range? Of course, the narrower, the better, right? Because here, if you have a narrower confidence interval, that means you have more accurate estimate. Okay, so here confidence interval based on the likelihood ratio test seems to be the best because it's from 0 to 0.074, but this one is 0.133. So this almost like a double. So you can see for a small sample size case, the likelihood ratio test is the best choice over the score and word test. And actually the worst test is word test. So that's why in practice, if you have a small sample size and also imbalanced, that means the pi is away from 0.5. It's close to either 0 or close to 1. Then you should use the likelihood ratio test. Okay, and both 3 tests depends on the normal approximation, rely on the central limit theorem. But the word test is the worst when we have a small sample size. Okay, any questions? Okay, I know sometimes you have questions and I didn't stop. And the reason is I think you will know the answers. Just listen. So sometimes you have to be patient. Okay. Okay. For the small samples binomial inference, and for the large sample inference, we'll need these because we have the normal approximation, as I said. And for the small sample size, then normal approximation will not be good. So instead, we should use the exact p-value. Okay, so what is an exact p-value? So exact means doesn't requires approximation. Just use the binomial to find out the p-value. Okay, so let's say if we have a coin flipped 10 times with 9 heads and 1 tail. Okay, so if the null hypothesis is 0.5 against not equals to 0.5, so we need to find out the p-value for this test. Okay, so here, an important concept is what is a p-value. You should know that because the prerequisite for this course is the 7005 and 15. Okay, so the p-value is a probability, right? But that probability is under the null hypothesis true or under the alternative hypothesis true? Is the probability under the null hypothesis true? So given the null hypothesis is true, the probability of observing what we got from the data, or even more extreme from what we got. And that is the definition for the p-value. Okay, so in other words, if the p-value is small, that means what we observed from the data is very unlikely to happen given the null hypothesis is true. So that gives us some evidence to questioning the validity for the null hypothesis. So that's the idea. Okay, so that's why we can reject the null hypothesis if the p-value is small. Okay, so the exact test, so the exact p-value here is what? We have flipped the coin 10 times, 9 out of 10 are heads. So what we observed is 9 out of 10, right? So what is more extreme? More extreme is all of them are heads, right? So the exact p-value will be what? Will be the probability of observing the y, that's the number of heads out of 10, is equals to 9, that's what we observed, and over 9, that's more extreme. And why we need to double it? The reason we should double it because the alternative is a two-way test. Okay, so the pi in the alternative says the pi can be either greater than 0.5, but can also be, the pi can also be less than 0.5. So it's two-sided. So that's why we need to double it, right? Okay. So in this case, we need to find out it's 2 times the probability of having the all 10 heads plus the probability of 9 out of 10 heads, right? So that's the exact p-value because we don't rely on any approximation. And that will be 0.02. Okay, but if the alternative is one-sided, then the exact p-value just be one side. We don't have to multiply by 2. So it will be 0.011. Okay? So for the discrete probability distributions, the small sample inference using the ordinary p-value. What is ordinary p-value? That's the one that I mentioned here. Is conservative. Okay. That is a term that we used very often in the statistical inference. You can hear, oh, this test is a conservative test, or this confidence interval is a conservative confidence interval. Oh, this p-value is conservative. And the opposite to the conservative is the liberal. Oh, this test is liberal, confidence interval is liberal, p-value is liberal. What does that mean in statistics? You should know that, okay? So here, let's say if a test is conservative, that means what? For example, I think you should all know the multiple comparison. Okay, if we do the ANOVA, we want to have some post-hoc test, and one of the approach we can do is Bonferroni test, right? And we know that if the number of tests is large enough, we know the Bonferroni test is a very conservative test. So what does that mean? Conservative. And we also know that there are some tests are liberal tests. Okay. So what does that mean? So a test is conservative. That means given the null hypothesis is true, the probability of rejecting the null hypothesis, okay, is actually less than the nominated alpha values. So that's how we say this is a conservative test. Okay, so like Bonferroni test, we have if we have a 95% family-wise error rate to be 0.05. Okay, and we know this Bonferroni is conservative. That means the actual family-wise error rate based on this Bonferroni test is actually less than 0.05. It's less than the nominated value. So that's how we call it a conservative test. And on the other hand, so a test is liberal, that means this one is greater than the nominal values. Okay, so a conservative test, that means it's very difficult to reject the null hypothesis. Then it should be. And a liberal test means it's easier to reject the null hypothesis. Then it should be. Okay, and I think if you use that idea, you can easily know what is a confidence interval is liberal and conservative. What is a p-value is conservative or liberal, right? And in Chinese, we have a saying that a good student will learn 10 related things if a teacher just teach one thing. So that's you have to think about. Like here, we say the p-value is conservative. What does that mean? That means the true p-value is actually what? Is greater than or less than? The true p-value should be less than. Okay, so that's how we say a p-value is conservative. So here, for the discrete probability distribution, especially for the small sample case, using the exact p-value is not good. It's too conservative. Okay, so we need to balance it. Okay, so we need to find a way to adjust the p-value. So a good way is called the mid p-value approach. So mid p-value approach, by its name, you know that. So we use half of the probability from what we observed, plus the probability that is more extreme. And that gives us the mid p-value. So in our example, what we observed is 9 head out of 10, right? So that's what we observed. So we only use half of the probability for y equals 9 plus the more extreme case. And that will be 0.006. And that's a better estimation. Okay, and so if we have a two-sided p-value, so it will be 0.012. So the inference based on the mid p-value compromise between the conservativeness for the small sample size method and the potential inadequacy for the large sample size method. So for the small sample size problem, it's the best one is to use the mid p-value approach. Okay. So the word test, we know that is the least reliable for the 3 tests. For the score and the likelihood ratio tests, based inference are better in terms of the actual error probabilities coming close to the nominal values. So the word test is the least reliable. Score tests and likelihood ratios are better in terms of the actual probability level. Okay, and if we found a difference, a big difference among these 3 tests, that's actually a warning to tell you that the distribution of the MLEs may be far from the normalities. So the normal approximation doesn't work well. So we should probably use the small samples methods. Okay, so in practice, if you apply these 3 methods, you found they are very different. So that is a warning sign that tell you should use the small sample size method instead. Okay. Okay. Any questions so far? Okay. For the for the intro lab, I showed you these 3, and also I have some examples to do the hypothesis testing. Okay, so you can take a look. Like here, we have a survey data. We have 837 replied yes, and 973 replied no to this question. And we want to test the pi equals to 0.5 against pi not equals to 0.5. Okay, so we can do as we can use the prop.test to test it. Okay, so this one shows you the it has some options. It has the with correction or not. And alternative is one-sided or two-sided. Okay, and if you want to know the details, look at the help menu. Okay, so and this is the test results. And this gives you the one-sided test. Okay, and this gives you the results. Okay, so this is the binomial test. Second. Okay, now let's talk about a natural extension of the binomial distribution. So the binomial only have two possible outcomes for each child, right? So what if we have more than two? And that's called a multinomial distribution. Okay, so the data is NIID trial, that's the independent and identical trials with more than two possible outcomes. Okay? And here, let C be the number of outcome category with the probability pi 1 through pi c. We have the summation of those pi's equals to 1. Okay. Okay, so among these m independent observations, we have nj that falls in, that's the number of observations that falls into the category J. Okay, and J is from 1 through C. If we add all the nj's together, we will have the n. That's the total sample size. Okay, so the probability of having this outcome, n1 through nc, equals to what? Equals to this one. So that's n factorial divided by n1 factorial, n2 factorial to the nc factorial times pi 1 to the power of n1 times pi 2 to the power of m2 up to the pi c to the nc. So you can see the binomial distribution is a special case, right? So the binomial distribution is a special case for the multinomial distribution when we only have c equals to 2. And this coefficient is called a multinomial coefficient. That's the number of ways to choose n1 of type 1, n2 of type 2, up to the n3 of type C from n objects. So how many parameters do we have for a multinomial? We only have c minus 1 variables. That's n1 through nc minus 1. And we have c minus 1 parameters. That's p1, but that it should be pi 1 to the pi c minus 1. Why it's c minus 1? Because we have the constraint from n objects and also the summation of the pi's j's equals to 1. So if we know c minus 1 pi's, then we know the one that we left, because 1 minus these c minus 1s will be the pi j for the one that we left. Okay, so the labels from 1 through c, these are arbitrary. You can change to different labels, that's fine. And the binomial is special case. The mean for the nj, that's the j's category count, is equals to the n times pi j, which is same as the binomial, right? And the variance is also same as binomial, n times pi j times 1 minus pi j. Standard deviation is the square root, okay? And the MLE for the pi j is the sample proportion. Okay? And the statistical inference, like the confidence interval and hypothesis testing, for a single parameter, pi j is the same as the binomial. We just merging all but the class J as one single group. Okay, so for the large sample test on the multinomials data, let's say, suppose the null hypothesis says the pi follows a certain values. And the alternatives is the is the contains the all parameter space except the pi zero that is specified in the null hypothesis. Okay, so that's the mathematical notation. It's the complement for the values specified in the null. Then we can have two large sample tests on the multinomial data. So one is the Pearson's chi-square test. Pearson's chi-square test has the test, the statistic is, we have J categories, okay? So J from 1 through C, or we have C categories. So that's the numerator is NJ, that's what we observed counts. So that's the observed counts minus the expected counts. Take the square, divide by the expected counts, and take the summation over all the categories C. Okay, and you may ask, what is the expected counts? The expected counts is based on this one. That's the mean of the NJ, that's the expected counts. Okay, so for a null hypothesis, we specified some value for the category 1, 2 to the C, right? So let's say for the category J, we have the proportion is pi j. Okay, and for the total sample size is n. So the expected counts for the category J is what? Is n times the pi j. And that is equals to the mu j. Okay, so that's how we calculate the expected counts. And this is what we observe from the data. Okay, so if the null hypothesis holds, the difference between the nj and the mu j will be what? Will be very small. Does that make sense? If the null hypothesis is true, these two values will be very much the same. Why? Because this is calculated based on the null hypothesis, right? And this is when the null hypothesis is true, nj should close to the expected value. So the numerator will be small, right? And take the square will be a small positive value. Okay, so if the null hypothesis holds, this x squared, the test statistic will be what? Will be small. Okay, if the test statistic is large, that means what? We have evidence to reject the null hypothesis. Yeah, right? And under the null hypothesis, okay, if we have a relatively large sample size n, we know that the x squared follows a chi-square distribution with the degree of freedom is not 1, but c minus 1. Okay, so that's the Pearson's chi-square test. Okay, so now let's see an example. In this example, we have this observed data. So we have 3 categories, AA, AB, and BB. So this is from experiment related to the genetics. So we have the 3 types, okay? And the null hypothesis, the probability of having the AA is 0.25 AB 0.5, and the probability BB is 0.25. Okay, and under the null hypothesis, we know that the expected count is what? Because the total n is 100. If you add all these together, you will see the total sample size will be 100, right? So the expected counts for the AA and the BB is 25, and AB is 50. And what we observed is 35, 43, and 22 for each, right? So the test statistic x squared is this divided by this plus this plus this. And do some calculation, you will find it's 5.34. Okay, and then we can do the chi-square test. Okay, so let's see here the tables. Where's the table? Okay, so for the chi-squares, we have the degree of freedom is 2, right? Because we have 3 class, C is 3, the degree of freedom is C minus 1. That's so we have what is the value we find? Find is 5.34. So what is the p-value? 5.34. You go to degree of freedom is 2, right? Go to the second row. 5.34 is between what? These two. Is that right? It's between these two. So the p-value is what? Is between, go to the top row. That's the probability on the right side. So the p-value should be what? P-value is between 0.1 and 0.05. Okay? So that's the p-value that we got. So the p-value is 0.069. But this is from the software. Okay? If you have these question in the exams, you can just write out the range, saying the p-value is between 0.05 and 0.1. That's fine. Okay? And what is our conclusion? The conclusion is if we set the alpha is 0.05, then we will fail to reject the null hypothesis. Although we see some evidence that the proportion do not follow 1:1 ratio. Okay. Okay. So I've already explained 3.84. That's for the first one. Can you explain why not? I think for the second question, it's easy. You can just try it. Do it by hand. If you cannot, you will know the reason, right? So that's an easy way. So this one, is that sometimes small, the small c stand for a certain, and C stand for the number of categories in the multinomial here, okay? Okay. So we can also do it through the likelihood ratio test. For the likelihood ratio test, the test is still the same. -2 times the log of the likelihood ratio. So the likelihood ratio is, the numerator is the likelihood value under the norm. The alternative is in the denominator, okay? So here, it's -2 times the log for the L0 to L1. And if the null hypothesis is true, then these two will be what? Very close, is that right? So the ratio will be close to 1. So this one, if it's close to 1, the log of a close to 1 value will be what? Close to 0, right? So this one will be close to 0. Okay? But if the null hypothesis is not true, then this one will be what? The L0 will be much smaller than L1. Is that right? So then, so the ratio will be close to 0. All right? So the log of the ratio will be a very large negative number. Is that right? Like negative 1,000. Because the L1 is much bigger than L0. Okay? And then if you take the negative 2 times this value, then it will be a very large positive value. So this gives us, we will reject the null hypothesis if the G square is large enough. Okay, so if the G square is close to 0, we fail to reject. If it's very large, we will reject the null hypothesis. Okay, and this one also follows a chi-square distribution with degree of freedom is C minus 1. Okay, but here we can also say it's the number of parameters constrained in the null hypothesis. This is more general definition, and you will see why in a minute. But most of the time, this one should be C minus 1. Okay? Okay, now let's see for the likelihood ratio test in the previous example. So in the previous example, we have these are the observed data. N is 100. The null hypothesis is this. And for the test statistic under using the likelihood ratio test is -2 times the log of, okay, that's L0. Okay, that's L0, that's under the null. And this is L1, that's under the alternative. Okay, under the null hypothesis, we have the pi value. Is that right? So we have 35 observed from the class 1. So that's 0.25 to the power of 35. Is that right? Times 0.5 to the power of 43. And times, that's the second class. And this is third class. Right? Okay. Over this. Why this is the denominator? Because what is the L1? L1 is the maximum likelihood value under the alternative. Okay, so that we should use the MLE because the MLE is the one that maximizes the likelihood. Is that right? What is the MLE for the multinomial? Remember, the MLE for the multinomial is the sample proportion, right? So that's why we have the 0.35 because that's what we observed. 35 out of 100. Is that 0.35? Yes. To the power of 35. And then 0.43 to the power of 43, 0.22 to the power of 22. Okay, so that is the likelihood ratio test statistic. But you may say, okay, wait, there's a problem. What problem? Because the L0, that's the likelihood value. But for the multinomial, we also have this part. We missed this part. Why I didn't use this part? Why I didn't include this part? The reason is this multinomial coefficient is a function of what? It's only a function of n and n1 through nc. Is that right? It's not a function of pi. It's not a function of pi j. So what does that mean? That means we have the same multinomial coefficient. for the L0 and for the L1. Is that right? If you don't know, if you are not sure, just calculate by hand. Just write it out. Try it and you will see. So it's the same under the no and under the alternative, because that's only based on what we observe. Okay, so since they are all the same, so we don't need to include. Why? Because this one is about the ratio. The ratio, we have the same part, it canceled out. So that's why I only include this part. Okay, so we got 4.96. Okay, 4.96, then we go to the chi-square. Degree of freedom is 2. 4.96 is between this. Still, so the p-value is 0.05 and 0.1. Okay, so that's based on the table, but software gives you the exact value. Okay, so it's 0.084. Okay, any questions? Okay, so you can see the chi-square, the Pearson's chi-square and the likelihood ratio test, they give you the very similar test statistic, and the conclusion are the same. Okay, so a question is, so this gives you the test statistic for the chi-square using the Pearson's and the likelihood. Okay, so which one is better? And what is their performance under different situations? Okay, so both tests are asymptotically equivalent. Okay, what does that mean, asymptotically? Asymptotically means that if the sample size, here the sample size is the total sample size, and goes larger and larger, these two values will be equivalent, converge together to the same values. Okay, so that's called asymptotically equivalent. But if the sample size is not that large, they can have different results and even can give different conclusions sometimes. Okay, so that tells us what? So we don't need to compare these two tests when the sample size is large. We only need to compare these two tests when the sample size is small. Does that make sense? So when we have a relatively small sample size, which one is better? So for the likelihood ratio test, the normal approximation on the chi-square approximation is actually relatively poor compared to the chi-square, Pearson's chi-square. In other words, for small sample size data, we prefer to use the Pearson's chi-square because the chi-square approximation for the using the Pearson's chi-square test give us better approximation, even though the sample size is small compared to the likelihood ratio test. Okay, but then you may ask, then why we need to have a suboptimal test, likelihood ratio test? We can always use Pearson's test. Why we need to have this test? There's always a reason. Okay, so next example give you a reason, because the likelihood ratio test is more general. It can be applied to more complicated case where the Pearson's chi-square test may not be available. Okay, so that's why the likelihood ratio test is one of the most popular tests in the statistics. So it has a reason. It's a very general test. The idea is simple and it can be applied to different situations. Okay, so that's the reason. So now let's see this challenging example. So we have 156 dairy cows, okay? And these cows were classified to whether or not they experienced pneumonia within 30 days of birth or 60 days of birth. And the calves that got an infection were then additionally classified to whether or not they developed a second infection within 2 weeks of the first one's resolution. So to do the test, here we are, the null hypothesis is the probability of getting the primary infection of the pneumonia is the same as the conditional probability of secondary infection given the calf got the primary infection. Okay, so that's the null hypothesis. So you can see this is a more complicated case. This is not like this example. We have an existing formula that we can plug in. Is that right? Like for this example, oh, it's easy. We can just plug in either the chi-square tests using the Pearson's, or we can do the likelihood ratio test because we have a formula and we can easily plug in the data, get the results. But for this one, we don't have such existing test, right? So we have to do something, okay? So first, let's just create a table. Okay, so we have first infection and the second infection, right? So for the first infection, we have two possible cases, yes and no. And for the second, we also have yes and no, right? So we have, what we observed is 30 calves have both pneumonia infections, first and second. And we have 63 calves that only got the first pneumonia infection, primary infection, okay? And we have 63 calves got the no pneumonia infection at all, have no first, no second, okay? And we don't have this one. Why? Because if we have no first infection, of course we don't have second infection. That's for sure, right? So this is the data what we have, okay? Now let's first find out what is the, so under this hypothesis, we need to find out what is the MLE, right? To have the, what we have. Okay, so let's first define the pi to be the probability of having the primary infection. Okay, and based on this, and also based on the null hypothesis, the probability of getting the primary infection is the same as the conditional probability of secondary, given the first. Okay, so then the probability of having the secondary infection will be pi squared. Does that make sense? So here, in the null hypothesis, okay, we said the probability of getting the infection, I1, okay, that's the primary infection, is pi, right? And is equivalent to the probability of getting the secondary infection given the first infection, right? It's the same as pi. That's the null hypothesis. Okay, so then the probability of having both infection, I1 and I2, is what? based on the definition, it will be what? It will be the probability of I1, is that right? Multiplied by the conditional probability of I2 given I1. Is that right? That's the conditional probability definition, right? So this one is pi, and this one is also pi. So the probability of having both infection will be what? Will be pi squared. I think that's obvious, right? So that's pi squared. And the probability of having only primary infection is this one. Why? And that's also very obvious. Because here, having the first infection but not the second is what? That means the probability of having the I1, but the complement of I2, that means have no infection for the second time. And that is equals to having the pi 1, or having the first infection multiplied by what? 1 minus the probability of getting the second infection. Is that right? That's I2 given I1. Okay? All right? And that will be 1 minus pi, right? And that is pi. So multiplied by this. So you can see it is pi times 1 minus, or pi times 1 minus pi. Okay? So that's this one. Okay? And then this one, this is the easiest one, right? So basically it's just the total. If you add all these three probabilities together, it will be what? It will be equals to 1. Does that make sense? Because that includes all the possible cases. This one is not possible. So it's just 1 minus this one and minus this one. Okay, you just do some calculation. It will easily get this one. So this one is the easiest to get if you know these two, right? It's just 1 minus. Okay. Okay, if you clear about this, then we can find out the MLE. How to find out the MLE? So we have the 3 situations, right? 3 categories. The first one is having the probability is what? Is pi squared. The second category has the probability is pi times 1 minus. The third one is 1 minus. Is that right? So then we can have the kernel of the likelihood. So the kernel means the core part, right? So it's the pi square, that's the category 1, means it has both infections to the power of n11 times this is only having the first infection, not the second, to the power of n12 times 1 minus pi. That means no infection at all to the power of n22 or n22, right? So the likelihood is what? It's the log of this, right? Actually, it's not that, this is not rigorous. So I should probably replace the equal sign to this one because I removed the multinomial coefficient part because that part is a constant. It's not a function of pi. So I take that away, okay? It's a constant. So then I take the derivative, first order derivative for the log likelihood, and it's this one, and I set to be 0. That's the old trick, right? To find out the maximum value, just take the first order derivative to set it to be 0, and then we just find out what is the pi. So to do some simple calculation, and you will see the MLE is what? Is this one. Very simple calculation. You can do that after class, okay? And this, in our example, it's 0.494. So that's the MLE for the pi. Okay? Okay, after that, we can also do the hypothesis test, right? So here, the total sample size is 156, okay? And the expected counts under the null hypothesis is this. So under the null hypothesis, what is the null hypothesis? So the null hypothesis says having the first pneumonia infection, the probability of having the first pneumonia infection will be the same as the conditional probability of getting the second, given the first infection, right? So the expected count will be this, this, and this. How do we calculate that? Because we got the MLE. MLE is 0.494. That's the MLE for the pi. Okay? And remember, MLE has a very nice property. I'm not sure if you, that's the property. I think I put it here somewhere. Let's see. Yeah, here, you see that? Invariance. What does invariance mean? I explained that when we talk about invariance means that if pi hat is the MLE for the pi, so the pi hat square is also the MLE for the pi square here. And that is based on the invariance property for the MLE. Okay, so that's why we can use this one here. That's also the MLE for the pi square. Okay, so we have that's the total sample size n multiplied by this, that's 38.1. And this is that. So these are the expected counts. So now we can use the Pearson's chi-square. Okay, so you can see we got this, and what is the degree of freedom? Actually, you can see we are not, the degree of freedom is not 2 anymore. And you may ask why it's not 2. Because here we have 3 possible categories, right? This, and this, right? And here you can say, why not using the degree of freedom is 2? Because based on here, it's the number of cells minus 1, right? But here we cannot, because we have an extra constraint. So we have basically 2 constraints here. One constraint is these 3 probabilities add to what? Add equals to 1. Is that right? And the second is, in the null hypothesis, the probability of getting the first infection is the same as the conditional probability of getting the second. So we have 2 constraints. So that's why we lost 2 constraints. So that is the reason why the degree of freedom is actually 1. Okay? So this is our test statistic. Of course, this is highly significant. Okay, this is highly significant, right? So we should reject the null hypothesis. Okay, so that means what? That means we have strong evidence to show that the conditional probability of getting the second infection is actually not the same as getting the first. Okay? Okay, so Does that make sense? Okay, and then you can think about one step further. So if we reject the null hypothesis, then what is the results? What is the data points to? So having the second infection, the conditional probability of getting the second infection is higher than getting the first or lower. Right? You can think about it. And that you can see from the data. So what we observed for the second, so in here, so here we have three categories. Thus, you can see the first one is getting both, and the second one is first and but not second, and the third one is neither. Okay, so you can see in this case, the probability. So what we expected is 38.1. So that's what we have for the for having both infections. But what we observe is below that. Okay, and also for the second one is having only the first infection, but not the second. What we expected is 39, but what we observed is 63. You can see there is a big difference. So what does that imply? So that means what? That means the probability of not getting the second pneumonia is actually much larger than what we expected. Right? So you can see the conditional probability of having the second pneumonia is actually less than the probability of having the first pneumonia infection. So the conditional probability of getting the second is actually lower than the first one. And that is what implies from the data. Okay, so this is the likelihood ratio test, and you can easily check that. It's not difficult at all. So you can find, so the test results are the same as the, okay, and this is the homework. So for the homework, I've already posted the homework, the PDF for the problems here. You can use that to find out the homework, okay? And I will launch assignment 1 in the Moodles, and you can submit that through the Moodles. Okay, so through this lecture, so through these examples, I want to tell you something that when you have a data set, when you do this test, it's not just running the software, getting the p-values, that's it. You need to have some statistical thinkings. Okay, it's not just, oh, we rejected null hypothesis, or we failed to reject. And you can have some one step further. So what does the data implies? Tell us. Okay, so and also I think this introduction, I'm actually at first I plan to have 2 lectures, but now I spend 3 lectures. So I will move faster and faster in the next in the rest of the chapters. So, but I think it's very important to go slowly for the first one. Okay, let me see any questions. Yeah, the homework is due for a week, so I will announce the homework once right after class. Okay, so it should be due next Thursday. No, next Wednesday. I'm sorry. Okay. Okay, let's stop here.